Hi, this is a video to help you remember the mechanisms for converting alcohols to alkyl halides using hydrogen halide acid. Let's start with a tertiary alcohol. A tertiary alcohol will react with an acid halide, an initial step where the electrons on the oxygen will attack the acidic hydrogen on the acid halide. So we're going to make a new bond between the oxygen and the hydrogen, and we're going to break the bond between the hydrogen and the halogen. Remember, I have two lone pairs on that oxygen that's doing that attacking. So this is my nucleophile and my electrophile. So I've just made a new bond here between the oxygen and a hydrogen, and I've broken the bond between the hydrogen and the halogen, so I left the electron pair on the halogen. I have a negative charge on the halogen and a positive charge on oxygen. And this is where the true mechanism here that distinguishes tertiary, secondary, and primary alcohols begins. So in this part of the mechanism, I'm going to break the bond between the carbon and the oxygen. And this step is carbocation formation. So I've broken the bond between the carbon and the oxygen, leaving only 3 bonds on this carbon, which is why it's positively charged. And now I'm left with water and my halide. This is not very stable, and so it's going to immediately react. The electrons on the halide are now going to attack the carbocation to give you your to give you your alkyl halide product. So your final products are the alkyl halide here and water. This initial step, step 1 here, is just protonation of the alcohol. And this, again, is where your true Sn1 type mechanism comes in, where you first generate a carbocation, and then that carbocation is attacked by the chloride here to give you your final product. So this part is what we really think of when we think of an Sn1 mechanism. Let's look at what a secondary alcohol would do. So in a secondary alcohol, you would have a very similar reaction. Your alcohol oxygen electrons are going to attack the hydrogen on the acid halide, and the electrons in this bond are going to be left on the halogen. This is the same first step as we just saw. You protonate the alcohol. And so in this case, I'm going to get a protonated secondary alcohol. Oops. And my halide is left over. And just like in the tertiary example, the next step is the first step of my Sn1 type mechanism, where the bond between the oxygen and the carbon is going to be broken, and I'm going to generate a carbocation. The biggest difference between the secondary and the tertiary alcohols is that they give you a secondary and tertiary carbocation respectively. And the relative stabilities of these two things is that the tertiary carbocation is much more stable than the secondary carbocation. And that's why the tertiary alcohol will actually react much more quickly than the secondary alcohol. We can use a reaction energy diagram to explain this in a moment. But let's finish the reaction first. So I've got water now and my carbocation, and now the halogen, the halide here, is going to attack that reactive carbocation. This is, again, a nucleophile attacking an electrophile. And my product is just the halogen now attached to the same place where the alcohol left. I can use a reaction energy diagram to explain the relative rates of these two things. So I'm going to put energy on the y-axis and the reaction coordinate on the x-axis. My reactants here, either the tertiary or secondary alcohol, probably have pretty close relative stability. So I'm just going to call this R. So everything here is reactants. So the alcohol and the acid halide. So I'll just draw that. ROH plus HX. My first intermediate here is just the protonated alcohol. And that actually has a little bit lower energy than the starting material. So when I draw the first step in this reaction, I'm going to call this intermediate 1. And that's going to be my protonated alcohol plus my halide. And now you can't just draw a straight line from the reactants to the intermediate. Remember, there's some activation energy associated with this little step. And so up here we have a transition state. And I'll call that transition state 1. So now the next step is for intermediate 1, or basically these things, to convert into the second group of intermediates. And this group of intermediates is a pretty high energy. And remember, these are carbocations. They're very unstable. So I'm going to put them much higher in energy. So I'm going to say here, this is my carbocation, so I'm going to say R plus X minus and water. Now, for the tertiary carbocation, I might put it here. But the secondary carbocation is less stable, and which means it has more energy. And so I'll put my secondary carbocation here. So there's two different, now I've distinguished between the two reactions. So for my tertiary reaction, my reaction profile might look something like this. And for my secondary reaction, the reaction profile might look something like that. Okay. And then the last step is pretty similar. You just have the halide attacking the carbocation and giving you your product. And I'm going to say that the two products have relatively close stability, and I'm just going to call this Rx and say that they're about the same. And so here we go. And here we go. All right, so the main difference between the energies of these two reactions is really in this second step, where you generate the carbocation. So the activation energy for the tertiary alcohol will be associated with this difference. And so that's the biggest hill we have to climb, and so that's the rate limiting step of this particular reaction. And so for the tertiary alcohol, you're going to have actually a lower activation energy than you would for the secondary. So I'm going to use a different color. I'm not sure if you'll be able to see it. This is yellow. Yeah, okay. So now the activation energy for the secondary carbocation to form is much larger than the activation energy for the tertiary carbocation to form. And so this is what gives you the relative rates. The fact that the tertiary alcohols react in this type of reaction much more quickly than the secondary alcohols will. It's because the tertiary alcohols don't have quite as big of a hill to climb compared to the secondary alcohols. And so the tertiary alcohols will always react in an Sn1 type mechanism faster than the secondary alcohols. Both of these reactions are Sn1 mechanisms. And remember that they're called Sn1 mechanisms because there's only one thing that matters for the rate law, and it's the concentration of the alcohol over here. So this alcohol is being converted into a carbocation in the rate limiting step. So our rate is equal to K, some rate constant, times the concentration of the protonated alcohol. And the fact that it's just this one thing that matters in the rate limiting step makes it an Sn1 mechanism. So now you can practice by taking these general reactions and applying them to other secondary and tertiary alcohols.